Okay, so before doing the reduction, showing the tree coloring is NP complete, let's maybe talk a little bit about why this problem is so important. So maybe the coolest application of graph coloring is register allocation. So the compiler, every compiler essentially needs to do register allocation, right? You generate the basic assembly code, but then you need to, you compute values and you need to assign the values to registers, right? So what the compilers do, they generate the a graph where you have the values that are being computed, and you put an edge between them if they cannot be in the same register because they're in conflict. And then you have this graph, and you now just color it because every color corresponds to a register that can hold this value, right? This naturally captures time issues because essentially something that is earlier in the code is not going to be in conflict with something later on because you save the value and so on. So the fewer color you use, the fewer register the code needs. Now what compilers do, if you don't have enough registers, you start doing things like storing values on the stack or in memory, which is much slower than using registers. Of course, it's not that bad because those values are going to the cache on the CPU, so it's still going to be reasonably fast, but it's definitely by order of magnitude slower than using registers. And so you really want to use as few registers as possible. I mean, you want to color the graph using as few colors as possible. Now, one of the big advantages of RISC versus CISC, so CISC is a complex instruction set, right? Is the classical approach in designing CPUs. One of the new component with RISC was that they allocated more registers. So suddenly there were many more registers, which means that the register allocation problem became easier, and that was one of the relative advantage. By now it might be less important, but it is what it is. Okay, this is just a formal definition of what I just told you about graph coloring. Here is another classical problem, class scheduling. You have classes, you need to schedule them inside room, for example. You cannot, two classes are in conflict if they're in the same time, or same instructor teaching them, or same student have to take them. So you build a conflict graph where every node is a class and every two classes are by an edge if they are in conflict for one of those reasons. And then you want to do coloring, and the coloring would correspond to what rooms to use, right? Where no two classes that are in conflict can be in the same room. So this is a classical, and this is kind of the standard thing, right? A lot of problems that arises are problems about resource allocation and taking conflict into consideration. Here is another example. You have antennas. Think about them as cellular antennas or Wi-Fi base station. You want to assign them frequencies such that no client can access two antennas that have the same frequency because they're going to interfere with each other, right? So you know the location of the antennas. You know which antennas are potentially in conflict because somebody can access both of them in the same time, and you create this interference graph between the base stations, and now you want to color it. The number of colors you need is the number of different frequency you will need to assign to those base stations. Right. Okay. So all those problems are graph coloring problem. I hope this convinces you that this problem is really important, graph coloring.